Hi, everybody. My name is Miha, and I'm a PhD student at the LMU in Munich and IQM Quantum Computers. And today I would like to present to you a recently published paper on neural network-based qubit environment characterization. First of all, as a brief overview, there are many different contributions to the noise that we typically observe in superconducting circuits, each with its own characteristics and different effects. I listed some examples here, such as strongly coupled two-level systems, slowly fluctuating, typically 1/f noise, more complex interactions of the qubit with quasi-particles, but other error sources also exist. Now, what is common to all of the major noise sources from the previous slide is that these environments are complex and rarely Markovian. So descriptions of our system in terms of standard Lindblad operators, or T1 and T2 times, will really fail to capture the detailed dynamics which we might be interested in. And since we are dealing with these complicated noise forms, and if we wish to describe them accurately, there are basically two ways of doing that. The first would be to find some kind of phenomenological description of the noise on our chip, or what we will focus on in this talk, we can choose a physically motivated model, which corresponds to a microscopic picture of the environment. Now, each of these two approaches has its pros and cons. For example, the effective description might be simpler when trying to describe different noise sources and is better suited for simulating the dynamics of our system, while the physical picture will give us a better idea of the nature of the noise, where it comes from, and also what we can do about it. Furthermore, since some of the environments presented here have more or less random parameters, being able to reconstruct them is beneficial if we want to maybe employ dynamical decoupling or error mitigation techniques in the future. Now, typically, it is possible to calculate the effect of a certain environment on a measurable quantity more or less accurately. However, what we are interested in here is whether we can do it the other way around. So can we extract some information from the environment based on a quick measurement of the qubit, which is basically used as a probe? There's a variety of techniques that one can employ for this task, such as just regular curve fitting, maximum likelihood estimation, or some type of machine learning. However, we decided to focus on a neural network-based approach since it offers the most flexibility. For example, instead of using it to just fit some parameters of a model to an observed coherence decay, we can also easily train it for other tasks. Now, what I want to focus on now is the pure dephasing decay of a transmon. So we start out with a measurement such as a simple coherence decay as observed in a Ramsey experiment or similar. And the workflow here is as follows. After the qubit coherence decay is measured, this curve is first processed via standard principal component analysis in order to try to reduce it to a smaller number of points with more informational value. Now, this set of points is then fed into a neural network, which is trained to give us some information about the environment. Now, more specifically, it can be used to find the parameters of a model which best describe the observed decay or compare different environmental descriptions to see which one is a better fit to the observation. Now, to elaborate further, let's look at some concrete examples. I mentioned earlier that we will analyze a pure dephasing decay, but even a pure dephasing decay has different contributions. You have a 1/f background caused by an ensemble of two-level fluctuators, superimposed with some Markovian background, and finally non-Gaussian random strongly coupled impurities, which will be the focus of this talk. In order to describe these impurities, we have studied two theoretical models, the first of which is a fully quantum model where an impurity is described by a two-level system coupled to its own bath. So the first task we will look at is whether we can reconstruct the parameters of these quantum impurities affecting the qubit from a single measurement of the coherence decay. The second model we consider is the more standard classical random telegraph noise, where a fluctuator is described as a stochastic process randomly jumping between two values. Since we can make some direct correspondences between the quantum and classical models, we can train the neural network to distinguish between a pure dephasing decay caused by a classical and a quantum environment. And lastly, we can try to characterize how quantum or classical an environment is when it is comprised of both classical and quantum impurities. So as the first task, let's look at how well we can reconstruct the parameters of the quantum model. So here, each impurity is characterized by three parameters, namely the energy difference between its two states, its coupling to its bath, and the coupling to the qubit. We have simulated a large number of environments with 5 impurities, and we will try to predict the parameters of the 3 most strongly coupled, while the remaining 2 are treated as background noise and model inaccuracy. The first issue that we noticed when implementing this naively is that directly reconstructing these parameters in the model does not yield good results. This is because some fluctuators have too weak of an effect on the qubit and are therefore extremely hard to reconstruct. Basically, if the effect of the impurity on the qubit is small, extracting enough information about the impurity is difficult. Now, for this reason, we renormalize the model parameters as shown on the slide in order to force the neural network not to pay too much attention to the impurities with a negligible effect. In the first column here, we can see that for all three effective parameters, the predictions generally do recreate the environment. But what is perhaps more interesting is the right column with panels D to F, where the relative error of the effective quantities from panels A to C is plotted versus the coupling parameter eta. Now, it is known that this coupling parameter determines how non-Markovian and non-Gaussian an impurity is, with the non-Markovian regime corresponding to eta similar to or larger than 1. Now, this coupling parameter can be intuitively understood since the non-Markovianity might arise due to strong coupling to the qubit, denoted by V, or long impurity timescales, denoted by gamma, which is directly related to the impurity BAF coupling T in this model. Now, additionally, we have heuristically added a temperature dependence, as we have observed that the impurities become frozen at lower temperatures, thus mitigating their effect. Now, interestingly, we observe a correlation between this coupling parameter and the relative error of the predictions. We are actually still quite bad at predicting weakly coupled impurities, but the accuracy improves as the dynamics become more non-Markovian and the backflow of information from the environment to the probe qubit increases. So the second task that we try to tackle is a classification task. So let's say that you have two candidate environment models, but you have no idea what the parameters for each should be. So there is no straightforward way of comparing them. Another benefit of using a neural network for this task is that the output is a probability distribution. So we also know when the predictions are uncertain. So here we tested the quantum and classical noise with consolidated parameters so that they result in similar qubit dynamics as seen here. This task actually turns out to be very easy for the neural network with accuracies as high as 99%, as seen here in panel C, even if the test sample contains a different number of impurities than the training samples. The accuracy falls to 95% if we consider only the second half of the decay curve, meaning that less information is given to the neural network, so this drop is expected. We can now try to make the classification task even a bit more difficult by considering an environment where some impurities are quantum and some are classical. We now wish to classify how quantum is an environment by trying to predict the ratio of quantum and classical impurities. For this task, we generate an environment of 10 impurities and try to classify the 5 most strongly coupled. Now, looking at the example decays here, this is a non-trivial task and the overall accuracy is noticeably lower than previously. But even though only about half of the decays are classified completely accurately, the neural network rarely misses by more than one impurity. As an example, looking at the confusion matrix in panel B, we can see that most of the values are concentrated around the diagonal where they should be. So what the color map of panel B actually tells us is the likelihood of a decay with the impurity ratio on the x-axis being classified as a decay from the y-axis. So each column is a probability distribution for a specific category of decays from the test set. So when a neural network is trained, it is basically taught to minimize a so-called cost or loss function. In the previous two examples, defining this loss function was simple. In the first example, it was defined as the mean squared error of the predicted versus actual impurity parameters. And in the second example, it was a binary cross entropy. In this case, even though it seems like it is a classification task, such as the previous one, the cross entropy function does not yield good result as it does not consider the similarity between the neighboring classes. For this reason, the loss function used here is a combination of both mean squared error and cross entropy. So now to sum everything up, we have shown the potential of neural networks to fit theoretical models to observe decays and also compare different theoretical descriptions of environments. Now, there may be no fundamental limitations to extending this procedure to larger and more complex systems, such as this 2-qubit gate pictured here. However, if we would want to characterize larger systems and more complex environments, it will become increasingly difficult to produce the large number of observables needed to train the neural network with a reasonable accuracy due to increased simulation complexity. Now, another consideration is that when in the future, hopefully qubit coherence times increase, meaning that the qubit environment couplings decrease, will the environment still have enough non-Markovianity and information backflow for accurate predictions? At this stage, we can assume that also slower fluctuators exist, which will induce non-Markovianity due to their long characteristic timescales. So we do not expect these non-Markovian effects to completely disappear. So this was everything from my side. Thank you for your attention, and I will be happy to answer any questions.